Take a look at your phone. Go on, nobody's watching, it's fine. Your teacher said so, you can look at it. Pretty sweet, right? Lights up, looks fancy. Let's talk about it. Okay, now you have to put your phone away. Seriously, go ahead. I know it's hard. Put it on. Okay, good. All right, now that your phone is away, let's think about your phone. How does it work? How is it that it operates day after day? Well, you know you have to charge it, but what does charging it do exactly? Well, it turns out it increases the electrical potential energy of its battery. You see, your phone has a lithium-ion battery, and when you plug it into the wall, it increases its electrical potential energy. And then you get to use it all day, using that potential energy to make electrons fly through your phone and give you that sweet display. Electrical potential energy is cool and important. Let's take a look at this lesson and learn all about electrical potential energy. Let's get started by reviewing our lesson objectives. First, we'll review potential energy in general. Then we'll introduce electrical potential energy specifically. And lastly, we'll calculate electrical potential energy. Here's some potential energy for you. This slingshot is pulled way back. And because of its arrangement, it has the ability to let that rock fly and to do work. Remember, energy is the ability to do work. And potential energy is associated with arrangement. So for example, this person has high gravitational potential energy after they jumped off the cliff, great move. And the reason is because of their height. The higher you are, the more gravitational potential energy you have. Remember, because we can calculate potential energy with this equation. Mass times the gravitational acceleration times height gives you potential energy. So the farther you are away from the surface of the Earth, the higher your potential energy. For example, if we pull a ball farther away from the Earth, that is, it's getting higher and higher up, in this case it would be well into space, the gravitational potential energy increases. It has all that way to fall and release that energy, so it has high gravitational potential energy. Electrical potential energy is the same. Here in the pink sphere, we have a negatively charged particle, and the yellow sphere, or yellow-orangish sphere, I suppose, is positively charged. They want to be near each other. And so when you pull those two charges apart, the electrical potential energy increases. And if we were to let them go, they would fall towards each other, much like the ball falls towards Earth. So when you have charges that are really far apart, they have high potential energy. The negative charge on the left and the positive charge on the right want to fly towards each other, and that's indeed what they'll do as they return to a lower potential energy state. In the meantime, though, you could do some work with them. So that's the whole idea. The farther apart that these charges are, the higher their potential energy. This is true very specifically for opposite charges. In other words, for positive and negative things, like shown here. Remember that it's going to take energy to pull those apart, and so as I pull them apart, I'm increasing their potential energy. But the opposite is true for positive charges, which experience repulsion. Here, if I push them together, I'm actually increasing their potential energy because they don't want to be together. They're going to fall away from each other, so to speak. So for the same charges, we have low potential energy when they're far apart, and if we squeeze them together despite what they want, they would have high potential energy. So the farther apart things are, the lower the potential energy for like charges, that is for the same charges. Here's the equation we can use to calculate electrical potential energy. Over on the left, we have potential energy. And then K, once again, is the Coulomb constant, and it's 8.99 times 10 to the 9th with a bunch of units, newtons meters squared per Coulomb squared. Okay, so this potential energy equation, let's say we're applying it to this situation, where Q1 is positive and Q2 is negative. Well, when I plug a negative sign into Q2, I'm going to get a negative potential energy. And that's what always happens when we have opposite charges. Opposite charges give a negative potential energy. What does that negative mean? It means it takes work to separate them. So as I pull them apart, that's actually going to take work. And that's what that negative sign indicates here. The opposite is true for two like charges. For example, here we have two negative charges, so Q1 and Q2 are both negative, and those like charges are going to give us positive potential energy. And what that positive sign means is that it takes work to bring them close together. So if I imagine two positive charges and I try to squeeze those together, it's going to take energy to do that. All right, well, all of this has a very practical application, and that's an atom. Here we have our simplest atom, hydrogen, with a proton and an electron. The charge on a proton is 1.6 times 10 to the minus 19 coulombs, and the charge on the electron is the same but negative, negative 1.6 times 10 to the minus 19 coulombs. So for the hydrogen atom, what do you think? Is its potential energy going to be negative or positive? Well, because it has opposite charges, it's going to have negative potential energy. That's actually true for all atoms. Atoms have negative potential energy. Let's actually calculate this potential energy. Let's put all of this to the test. This problem says, what is the electrical potential energy of the hydrogen atom given that the electron has a charge of minus 1.6 times 10 to the minus 19 coulombs, and the proton has a charge of 1.6 times 10 to the minus 19 coulombs? The proton and the electron are 53 pm apart. That pm stands for picometers, which is a really small distance. Let's start with a picture. In our hydrogen atom, we have a nucleus at the center, which is made of just one proton, and orbiting around it, we have an electron. And we're told that the distance between these two is 53 picometers, so a very small distance indeed. We want to know what the potential energy of this atom is. And if we take a look at our potential energy equation, we see that the first variable listed is Q1. So let's go ahead and assign Q1. We'll just take Q1 to be the first charge given, which is that of the electron, minus 1.6 times 10 to the minus 19 coulombs. Now, it doesn't actually matter which charge we assign as Q1 and Q2, because we're just multiplying Q1 and Q2. So if we flipped the order, that wouldn't be a problem. In any case, I'll take Q2 to be the second charge listed, which is the proton, which has the same charge but now with a positive sign, 1.6 times 10 to the minus 19 coulombs. Okay, what about our distance? Well, we're told that the distance is 53 picometers. And we're also given an equality at the end of our problem that 10 to the 12 picometers is equal to 1 meter, which is a good hint we're going to need to use that conversion. And of course, if we look at the Coulomb constant, we see that it has meters in it, so we need to take this to meters. So we'll divide by picometers, and we'll go to meters. 1 goes with meters, just like we see up in our equality here, and 10 to the 12 goes with picometers. So when we take 53, and we divide by 10 to the 12th, we're going to get a very small distance of 5.3 times 10 to the minus 11 meters. That means there's just a very small fraction of a meter between our proton and electron, which makes sense because this is an atom, it's going to be really, really small. All right, let's calculate the potential energy now. First up in our equation, we get K, which is our Coulomb constant, which is listed right here, and that's 8.99 times 10 to the positive 9th. Then we have Q1, which is minus 1.6 times 10 to the minus 19. Then we have Q2, which is positive 1.6 times 10 to the minus 19. Now, to make sure you don't get confused and think this is actually subtraction, it's not a terrible idea to put that negative number in parentheses, just to make you realize that you're multiplying by a negative number, not suddenly subtracting in the middle of your problem. And then we're going to divide all of that, just like in our equation, by distance, which is 5.3 times 10 to the minus 11. Here is another good case where you should use parentheses. If you don't use parentheses on the bottom when you plug that into your calculator, it will actually end up dividing by 5.3, but then multiplying by 10 to the minus 11th. So definitely grab your calculator and check that you get the same answer as me. If I'm putting this in my calculator, I'm going to put 8.99 times 10 to the 9th times a negative 1.6 times 10 to the minus 19th times 1.6 times 10 to the minus 19th. Then I'm going to go ahead and click enter. Then I'm going to do divided by, open parentheses, 5.3 times 10 to the minus 11, close parentheses. If you do that, you should get negative 4.34 times 10 to the minus 18. We'll talk about what that means in a second. If you didn't get that, Then go ahead and try punching it in your calculator again until you do get that. Even rewind the video and listen to me list exactly what to put into your calculator and copy that. It's a really important skill to learn to use that calculator well, and not always easy. Okay, well, first let's round for sig figs. Our charges and our distances all have 2 sig figs, so we're going to keep 2 sig figs. And that means we're going to go ahead and round this to minus 4.3 times 10 to the minus 18. And we're dealing with energy here, so our unit is going to be joules. And that's the potential energy. Now you might be like, hey, that's negative. That's a little weird. But remember, when a potential energy is negative, what that means is it will take energy to pull them apart. And that certainly seems right. It's going to take energy to pull apart the electron and the proton. That's why they stick together and make an atom. Now it's your turn to give this a try. This says, what is the potential energy of the He plus ion, that is the helium ion, with an electron with a charge of minus 1.6 times 10 to the minus 19 coulombs, and a positively charged nucleus, which has a charge of 3.2 times 10 to the minus 19 coulombs. The nucleus and electron are 26.4 picometers apart. Okay, pause the video and give it a try. The answer you should have gotten was minus 1.7 times 10 to the minus 17 joules. If you didn't get that, pause the video and see where you might have gone wrong. Let's review what we've learned. First, we reviewed potential energy, where we saw that potential energy is energy associated with arrangement that can do work. And this applies to electrical potential energy. We introduced electrical potential energy, which is the energy due to the arrangement of negatively and positively charged particles. And lastly, we calculated electrical potential energy. Hey!